Our next topic is geometry in 3 dimensions, and we're going to start with some definitions again. A simple closed surface has one exterior, one interior, and no holes. So this die would be an example of a simple closed surface, as well as this basketball. The birdhouse, on the other hand, is not a simple closed surface because it's not closed. It has a hole in it. A solid contains all the points on a simple closed surface and all of its interior points. So in this case, the die is a solid because all of the material inside the outside of the die is the same as the material on the faces of the die. But the basketball is not solid because inside the basketball there's air. There isn't more of the material that makes up the exterior of the basketball. A polyhedron is a simple closed surface made up of polygonal faces. Here's one example of a polyhedron. It's a cube. It's probably the one that you're the most familiar with. Let's rotate it a little bit so that you can see that what makes a cube is that all of the faces are squares and all of the angles where these faces meet are right angles. This is a tetrahedron. Its faces are made up of equilateral triangles. This is an octahedron. It has 8 faces that are made up of equilateral triangles. This is a dodecahedron. It has 12 faces, and all of its faces are regular pentagons. This one is an icosahedron. An icosahedron has 20 faces, and each of its faces are made up of equilateral triangles. And the website that we're using to take a look at these three-dimensional objects and be able to rotate them is from Illuminations. It's called Geometric Solids. So if you'd like to play with these shapes yourself, just do a Google search for Illuminations and look up their Geometric Solids. Now we're going to start with the tetrahedron. Here's the tetrahedron on the Illuminations website. Let's start by counting the number of faces it has. So it has 1, 2, we'll rotate it, 3, and we'll rotate it again to find that it has 4 faces. Now the edges are those line segments that connect the faces together. So let's count the edges on the tetrahedron. I'm going to turn it this way so that you can see 1, 2, 3, 4, 5, 6. It has 6 edges. The vertices connect the edges together. So the vertices are 1, 2, 3, 4 points. So a tetrahedron has 4 faces, 6 edges, and 4 vertices. So let's put that information in our table. The tetrahedron had 4 faces, 4 vertices, and 6 edges. Now let's try the same thing with a cube. Let's start by counting the faces on the cube. So it has 1, 2, 3, and I'll have to rotate it to see the others, 4, 5, 6. So a cube has 6 faces. The edges are the line segments that connect the faces, so let's count those. So let's see, across the top it has 1, 2, 3, 4 edges, and around the bottom it has 1, 2, 3, 4 edges, and then around the sides it has 1, 2, 3, 4 edges. So the cube has 12 edges in all. Now if we count the vertices, I can see that on the top of this cube we have 1, 2, 3, 4 vertices. And on the bottom of the cube we also have 1, 2, 3, 4 vertices. So that is a total, there it is, that's a total of 8 vertices. So back to our table, the cube had 6 faces, 8 vertices, and 12 edges. Let's try the octahedron. The octahedron has faces that are equilateral triangles. So let's count them. I'm going to kind of rotate it this way so we can see all the triangles on the top. So there's 1, 2, 3, 4 faces on the top part. And then let me rotate it this way so that you can see 1, 2, 3, 4 faces on the bottom part. So that's a total of 8 faces. Now let's count the edges. So I'm going to rotate it to the top again so we can see there's 1, 2, 3, 4 edges on the top. Let's take a look at the bottom. There's 1, 2, 3, 4 edges on the bottom, and connecting the top and the bottom we have these edges, 1, 2, 3, one more, 4. So that was 12 edges in all. Now let's count the vertices. This time I'm going to go around this middle part. So we have 1 vertex, 2, 3, 4 vertices around the middle part. Here's 1 more at the top, and 1 more at the bottom. So that was 4 around the middle, 1 at the top, 1 at the bottom. That's 6 vertices in all. Adding that to the table, we have 8 faces, 6 vertices, and 12 edges for the octahedron. Now the dodecahedron, I'm going to go ahead and just fill in the table. If you'd like to actually count the faces, vertices, and edges, go to that Illuminations website and play with this yourself. You'll see that you have 12 faces, 20 vertices, and 30 edges on the dodecahedron. Now the number of faces, vertices, and edges actually has a pattern to it for these polygons. And that pattern was noticed first by a mathematician named Euler, who came up with Euler's formula, which is that the faces plus the vertices will always equal the edges plus 2 for a polyhedron. So take a look at, for example, this dodecahedron. It has 12 faces. It has 20 vertices. 12 plus 20 is 32. And that is the same thing as the number of edges, which is 30 plus 2. So for any polyhedron, this relationship will always hold between the number of faces and vertices and edges. We've seen some names for some specific types of polyhedron. Let's look at some other ways to name polyhedron. Prisms have two congruent faces, which are called the bases, and it's the bases that give the prism its name. All of the other faces that connect up those bases are parallelograms. Here's an example of a prism. It's called a triangular prism because the two congruent faces are the triangles that you see in the front and the back of this prism. That's the blue face that you see closest to you. And the faces that connect up those bases are the parallelograms or rectangles, possibly it's rectangles, that are connecting up those triangular bases. These are also prisms. They're both hexagonal prisms because the bases, those two bases that are congruent, are hexagons, and the shapes that are connecting up the hexagons are parallelograms. Be careful with the word base. Base does not mean bottom. In fact, if you look at these two hexagonal prisms, you'll notice that the bases on both of them, which are hexagons, are not necessarily on the bottom of the figure. The one on the left, the faces actually seem to be kind of on the sides as we look at them. So base for a prism simply means those two polygons that are exactly the same shape, that are connected up with the parallelograms. Now, saying that those bases are connected with parallelograms is exactly right, but sometimes the parallelograms that connect up the bases are actually rectangles, and in that case we call that a right prism. And if the shapes that are connecting up the bases are truly parallelograms that are not rectangles, then we call that an oblique prism. So in this case we have an example of a right rectangular prism and an oblique rectangular prism. Sometimes the oblique prisms kind of look like they've been pushed over a little bit. That's what makes those faces that connect up the bases parallelograms instead of rectangles. So if we go back and look at these pictures again, we can actually call this one a right triangular prism because the faces that are connecting up the triangles that are the bases are rectangles. And these are right hexagonal prisms. Once again, because those faces that are connecting up the hexagons that make up the bases, those faces are rectangles. Pyramids have only one polygonal base, and it's that base that gives the pyramid its name. A pyramid also contains a point that's not in the plane of the base, and all of the other faces that connect that point up to the base are triangles. This is probably what you think of when you think of a pyramid. It looks a lot like the Great Pyramids of Egypt. It's a right square pyramid because the base is a square. And it's a right pyramid because unlike this oblique square pyramid, the right square pyramid has that vertex that's not in the plane of the base, directly above the center of the square that makes up the base. You can see the oblique square pyramid has that vertex kind of pushed off to the side, so it's not exactly over the center of the square base. Here's an example of a right hexagonal pyramid. Hexagonal because the base is a hexagon. There are also solids which are not polyhedra. In other words, the faces aren't all made up of polygons. Cylinders are one example of that. they have two congruent non-polygonal bases and a surface that's generated by the edges of the bases. So when you think of cylinder, this is probably what you think of. This is a right circular cylinder. It's made up of two bases that are circles. They're connected with a curved face, and it's a right circular cylinder because those two circles that make up the bases are directly over each other, and you can see that the line segment that connects up the centers of the circle are actually at right angles to the radius of the circle. This is an oblique circular cylinder. It kind of looks like that right circular cylinder that's been shoved off to the side. This is a cylinder as well. Remember, to be a cylinder, it simply has to have two congruent non-polygonal bases, and those strange looking kind of bean-like shapes that you see that are parallel to each other are the bases. So it may not look like what we think of as a typical cylinder, but it does meet the definition of a cylinder. Cones have one non-polygonal base and a point that's not in the plane of the base. So this is probably what you think of with a cone, and that certainly is a very typical shape that we would think of for a cone. That would have a circular base and a point that's not in the plane of the base. Just like the other shapes, we can have a right or an oblique version of that. The right circular cone has that point that's not in the base directly over the center of the circle. So you can see that when it comes to three-dimensional geometry, we've also got a lot of definitions that we have to know and apply to these shapes. We'll be using some of these notions of three-dimensional geometry again when we talk about surface area and volume later on.